In our last video, we learned electricity leaves a power plant at hundreds of thousands of volts, but by the time it reaches your phone charger, it's just 5 volts. How does that happen? How does the same electricity shrink from 400,000 volts to 5 with almost zero energy lost? The answer is a device so elegant, so perfectly designed, that it has barely changed in over 140 years. It's called a transformer. And in this video, you're going to understand exactly how it works. Not just what it does, but the physics behind it. Before we get into the science, let's establish what a transformer actually is. A transformer is an electrical device that transfers energy between two circuits, and in doing so, it can change the voltage level. It can step voltage up from low to high, or step it down from high to low. Step-up transformers are used at power plants to push electricity across long distances at high voltage. Step-down transformers bring that voltage back to safe, usable levels for your home, your school, your factory. But here's the critical thing to understand, and this is something many people get wrong. A transformer does not work with direct current, DC. It only works with alternating current, AC. Why? That's exactly what we're going to find out. To understand how a transformer works, we have to go back to 1831, to a discovery made by a British scientist named Michael Faraday. Faraday discovered something extraordinary. A changing magnetic field can create an electric current in a wire that isn't even touching the source. This is called electromagnetic induction. Let me show you what this means. Imagine a coil of wire connected to a battery. When current flows through this coil, it creates a magnetic field around it, invisible lines of force that radiate outward like the field around a magnet. Now, place a second coil of wire nearby. If the magnetic field is constant, nothing happens in the second coil. No current, nothing. But if the magnetic field changes, if it grows stronger or weaker, that changing field cuts through the second coil. And this forces electrons inside it to move. A current is induced. This is Faraday's law, and it is the entire foundation of how a transformer works. The mathematical expression of the law is elegant. The induced voltage, EMF, equals the number of coil turns, multiplied by the rate at which the magnetic flux is changing. More turns. Faster change. Higher voltage induced. But why is there a negative sign in the formula? It shows that the induced current always flows in a direction that opposes the change in magnetic flux. Now, do you see why AC is essential? AC current is constantly alternating direction, 50 or 60 times every second. That means the magnetic field it creates is also constantly changing. Exactly what Faraday's law requires. DC current is constant. The magnetic field it produces is static, no change, no induction. The transformer simply doesn't work. Now that you understand the principle, let's look at the physical structure. A transformer has 3 essential parts. First, the primary coil. This is the input side. A C current enters here. It creates the alternating magnetic field. Second, the iron core. This is made of laminated silicon steel. Its job is to concentrate the magnetic field, to channel it efficiently from the primary coil to the secondary coil, like a highway for magnetic flux. Third, the secondary coil. This is the output side. The changing magnetic field, guided through the core, induces a voltage here. This is where your usable electricity comes out. The genius of the design is that the two coils never physically touch. Energy passes between them purely through the magnetic field, through invisible force. Now, we reach the heart of transformer theory, the turns ratio. The number of wires, turns in the primary coil versus the secondary coil determines everything. The output voltage, the output current. The relationship is beautifully simple. V1 upon V2 is equals to N1 by N2. V1 is the primary voltage. V2 is the secondary voltage. N1 is the number of turns in the primary coil. N2 is the number of turns in the secondary. Let's use a real example. Suppose a transformer has 1,000 turns on the primary side and 100 turns on the secondary side. The turns ratio is 10 to 1. If you input 11,000 volts on the primary, your output voltage will be exactly 1,100 volts. The voltage dropped by a factor of 10. Now, here is something crucial. And this is where many students stop and think carefully. Energy must be conserved. A transformer cannot create power. So if voltage goes down, what happens to current? Current goes up by the same factor. V1 I1 is equal to V2 I2. Power in equals power out. For an ideal transformer, efficiency is 100%. In reality, it's typically 95 to 99%, which is extraordinary. So far, we've been talking about an ideal transformer, one with no energy losses. In the real world, no transformer is perfect. There are two main types of losses. First, copper losses, also called I²R losses. The wire coils have resistance. When current flows through resistance, heat is generated. That heat is wasted energy. This is why high-voltage transmission lines carry electricity at very high voltage and very low current. Lower current means lower copper losses. This is the entire reason transformers exist in our power grid. Second, core losses. These come in two forms. Hysteresis loss. Every time the magnetic field in the iron core reverses direction, 50 or 60 times per second, the tiny magnetic domains inside the iron have to flip. This takes energy. It shows up as heat. Eddy current loss. The changing magnetic field also induces small, circular currents within the iron core itself. These are called eddy currents. They produce heat, which is wasted energy. This is exactly why transformer cores are made from thin, laminated sheets rather than solid iron. By dividing the core into thin layers, separated by insulation, eddy currents are dramatically reduced because they have no large continuous path to flow through. Transformers are everywhere, most of the time invisible to us. In the power grid, massive step-up transformers at power stations raise voltage to 400,000 volts or more for long-distance transmission, because high voltage means low current, and low current means low energy loss over thousands of kilometers. At substations near cities, step-down transformers reduce voltage to 33,000 or 11,000 volts for distribution. On the street, small distribution transformers, those cylindrical units you see on electricity poles, reduce voltage to 230 or 120 volts for homes. Inside your phone charger is a tiny transformer, converting 230 volts AC to 5 volts DC for your device. In hospitals, isolation transformers protect patients from electric shock. In electric vehicles, transformers are part of the onboard charger system. The transformer made our modern electrical civilization possible. Without it, powering cities from distant power stations would be economically and physically impossible. If this video saved you hours of textbook reading, smash the like button, share it with someone who's studying electronics or physics. Until next time, keep questioning how things work.